Hello, everyone. My name is Henry Bright, and welcome back. I'm going to be going over Project 2 for EAS3810. This is Part 2. Like I explained, we're doing this for 4 different objects in the wind tunnel. So in this video, I'm going to be going over how to do it for the airfoil. We're going to get the static pressure and velocity contours, the streamline patterns, as well as the drag force, and show you how to calculate the drag force coefficient. So in this case, you can see you can choose any airfoil for this project. I chose a NACA 2415 airfoil. So if you go to that website that's linked there, or if you go directly to airfoiltools.com, that's another link. I guess there's both. There's also this UC website. I believe that's the one that's attached. Doesn't really matter either way. Basically, what you can do is you can come in and you can go to NACA. If you scroll down and find it, 2415, you click on the DAT file, it gives you this, which is this full document. And basically what you want to do is start a new text document to put in these coordinates. So I'll show you what that looks like, just like that. Same exact thing, just in a text document. And then what you want to do is actually open this in Excel. So if you close the file and open it in Excel, it'll have some formatting issues at first maybe, but if you import it correctly, then you'll get what you're looking for. So like if I open, let's see, this is skipping ahead, but if I were to open it, open the text document. I don't think so. I think it's on my desktop. There it is. You can see I want to import it, but I'm going to want to import it. And this one I had already made some modifications to, so I apologize. But basically it would look like this. You would just get these. I've made some modifications to this, and I'll explain why right now. But basically you get the coordinates in here. It's exactly what we want. It goes from basically, what is it? It goes from the trailing edge over the top surface, and then comes back to the leading edge and goes around the bottom surface until you get back to the trailing edge. So that's what we want. And then we're gonna have to scale this. So again, going back to our blockage ratio issue that I've mentioned before in the last video, we want it to be less than 10%. 7.5% sometimes is the value that you're given, and I think that's what Dr. Osbey said as well, but I ended up just using 10%. Shouldn't be too much of an issue, but basically what that means is I want that cord length to be is kind of the critical length here that I'm looking at. So in this case, it's 10% of the height of the test section, which was 0.1524 meters or 6 inches. So I get 10% of that, it's 0.01524, and that's going to be our scaling factor. So it's really easy in Excel because you can just multiply all of these columns by that scaling factor. And so then you end up getting like something like this. There's all of our coordinates. But then there's some formatting issues with Fluent. So the important thing to know is I'm going to go over to my other Excel document to show this and show you what it should look like. Ultimately, you're going to want it to look like this. And basically what it is first column, which I think represents X, if I'm not mistaken. Could be wrong on that. You want all ones. Second column, which I think is just point number, if I'm not mistaken. Again, could be wrong. You want it in an ascending sequence, so 1 through, I think we have 61 points, 1 through 61. And then you have your coordinates, so we've already got them scaled. I just copied just copied the values only into this Excel sheet to have these, so it didn't carry over the formulas that I used with the scaling factor. And then your last column, which I think is Z, should be all zeros, because we are just in the XY plane. So that's exactly what you want that file to look like. So you want to save that. And in this case, I named it NACA 2415 to make things easier. I know exactly where it's located. That's important, and I'll show you why. So let's go ahead and get into Fluent. So if you open up your design model or geometry, again, like I said in the last video, I've already got the wind tunnel pulled up. Not going to do that in this video. Don't want to make it super, super long. So we're not doing that. Anyway, what we're going to do now to go ahead and get this airfoil, and there's several steps that we have to do to actually get this imported. So the first step is going to be create and point, and this is how we're going to import all of our points. So you can see it's from coordinates file is what it says. And this is where we're going to add that file that we just created. So mine, I'm just going to open it up right from here. And then if you go ahead and hit generate, boom, look at this. I'm going to have to zoom in to show you, but I'll have to move hand around a little bit. Oops. Why does it keep zooming? There we go. Beautiful. So that's our points. Exactly what we want. Okay. So that's our first step. Next step is we want to create a 3D curve. So we're going to go to concept, 3D curve. And that's going to create this curve through these points basically. And then this gets a little annoying because you have to literally select every single point on here. I've tried the box select tool and there might be something I'm missing, but I have not found a way to be able to select all the points just in one fell swoop. I've had to select them manually. So this will take a second. I do apologize. Feel free to skip through this video. I'm probably not going to say anything important. All right, well, we're going to restart. Very tedious, very boring. I'm sure I'm just stupid and there's some way to do this without having to select every single freaking point, but I have not been smart enough to discover it, so this is what we're rocking with. I'm very much a fluent novice. Know enough to get by. Okay, now we've got all the points finally working. There we go. And that's exactly what we want. So go ahead and hit generate. Boom, we have our 3D curve. However, we do need to point out something, and notice something. And I don't know if this arrow is going to be blocking it, but it is important. Let's see. Yep, and you can see it right here. So see the discontinuity here? So there's one important thing we need to do before we move on, and it's to fix this discontinuity. You can see the shape's not perfect, and that's because it's just the sketch is not going to be completely perfect either way, but it's going to give us the general shape we want. But yeah, the important thing here is we need to finish out the sketch and complete it so that it's a closed surface. So the way we're going to do that is we're going to go ahead and do concept lines from points, and we just select our 2 points here. So this one and this one, very hard to see here, which is very annoying. We got those two and hit apply and then generate. And now we have basically a complete surface with those two. So then our next step is going to be to create a surface where this airfoil is. So we're going to do concept, and it's going to be surface from edges. So a little different than what we've done before. And we have to select our 2 edges. So we're going to have this one, that small little line, and then we'll also have our major edge right there. So that's why I stayed zoomed in, because I knew I was going to need that. And I'll go ahead and hit apply and then generate. And you can see we've got a nice little surface generated here. Super helpful. So the next thing then is going to be to do a surface sketch on like our whole wind tunnel, like we've done before. So if I go to concept, surface from sketches, this is just the exact same thing as we've done before. With our wind tunnel in general, go ahead and highlight all of it, hit apply and then generate. And you'll see there's one surface for the normal wind tunnel, but if you zoom in, you can see there's a different surface here. But we need that to be an empty surface. So the way we're going to do that is to do a Boolean, which is basically going to subtract the 2 surfaces from each other, more or less. So I go ahead and go to create and then Boolean. And you need to change the operation from unite to subtract, because we want to subtract these. So if we do, our target body is just going to be the wind tunnel body. Which, I need to get rid of my box select. Single select, apply, and then our tool body is going to be where our airfoil is, that sketch. And if we hit generate, there we go. We've still got our surface sketch around there, but it's subtracted off this area of the airfoil where our sketch is. So that's exactly what we want. And that's really all that's different for the airfoil. There's definitely more of a challenge. There's more steps to it than doing some of our other objects, but really that's all there is otherwise. So we've kind of finished that out. You got through the hard part, guys. The rest of it's going to be much simpler. It's going to be basically all the same as what we've done before. So we'll go ahead and open up our mesh and get started with that. And like I said, we're literally going to do the same things that we've been doing. I probably shouldn't even go through all of this because it's kind of a little bit of a waste of time, but I'm going to at least progress through it to show you guys the solution, make sure you know how to get it, and kind of discuss what everything looks like, and make some comparisons to the other object that I tested in the last part of the video, which was that half circle with the leading edge being like that vertical edge. And you could see a lot of pressure drag in that. We're going to kind of compare what the airfoil does, because it's going to be a good bit different from what that cylinder did. You can see our cylinder is still in there from the last video. It'll update the mesh and update the object here in a second. There you go. There's our airfoil. So that's what we like to see. So yeah, we'll go ahead and do the same exact things that we've been doing. I'm not going to spend a lot of time talking about this. Just got to apply that all triangles method to this, our new surface. Go ahead and do that, and we'll hit generate to get our mesh. You'll see maybe a little bit of a difference here in the mesh, because it actually does kind of a nice thing for us where it kind of refines the mesh even more right around the sharp edges of the airfoil, which is kind of cool. I'm gonna show you that. You can see from a distance it basically looks the same, but look at this from a distance here. Look how more dense the mesh is around the airfoil and around the edges of the airfoil. So that's going to be helpful for us obtaining more accurate results. So that's a good thing. And then the next thing we're going to do is we need to update those name selections just like always. So velocity inlet, got it, pressure outlet, got it. And then the wind tunnel wall. And then lastly, our flat plate wall. And this one's going to be a little tricky again because we need to get both of those lines. Remember that we've got two lines essentially here. So we're going to have a really small one, which is going to be very hard to select. We need to zoom in even more and move myself around here. This is going to be very tricky to select. Let's see, did I get both? I think I did. Yeah, I think I got both. Looks like we're okay there. That's a little tricky. And I could be wrong, and that might throw things off a little bit, but it looks like I think we're good. So yeah, that's everything with that. Let's go ahead and update that in our workbench. Update our mesh, get the name selections and everything updated. Awesome. And now we move on to our setup. Go ahead and get some results here. All right. Again, I mean, basically everything's kind of going to be the same here as before. Not a lot's going to change. I'm not going to go through all the things because I've already got the, it's going to load in the same boundary conditions that I already had. It's going to load in the same energy equation, the type of flow, all that fun stuff is going to be the same as before. So I'm not going to bother showing you all that. I'm just going to initialize it and run the calculations so we don't waste more time. If you need to go back to a previous video to see how to do that, feel free, but I'm not going to run through that again. I'm going to try and keep this as short as possible because I'm sure it's already getting a little long anyway. And I want to get to the results because that's going to be the important part to talk about and kind of comparing what it looks like compared to our other shape that I did in the last video. Because we want to make sure we have results that make physical sense, and we want the meat of this project is actually comparing the different shapes and what kind of patterns you're going to get around them, what the flow is going to look like, what's going to happen, what the drag is going to be like. So we'll go ahead and initialize, and then got that done. So now we're going to run the calculation, and then we'll have to wait even more. Yeah, I wish I was a little more tech savvy or had more time to do this because it'd be nice to skip through this part of the video a little bit quicker, but it is what it is. We can deal with it. Feel free to skip ahead. Go ahead, start looking at the results. I'll talk about that as soon as this is done. So if you want to skip ahead, feel free. Otherwise, you can just chill with me. I'm not gonna do anything or say anything super interesting. I feel like I'm talking to myself right now, because I kind of am. But how many of you are actually watching this? Probably not many. If you are, congratulations. So close. There we go. That's what we like to see. All right. So let's do some analysis. Let's look at some of our contours first. Static pressure. Let's take a look at that one. Go ahead and display this one just like normal. Looks pretty good. Looks very similar, you can see, because the object's pretty small. And it's also not a bluff body. So you can see it looks pretty similar to what our normal wind tunnel results were. But let's go ahead and zoom in to take a look at the airfoil a little better. Nice. Okay, so you can see static pressure, you can see you reach kind of your stagnation point at the leading edge of your airfoil generally. So you can see this big region where you've got like a high pressure region. That's going to literally be like your stagnation pressure. So it's going to be kind of your highest pressure on the object there. And then you can see kind of the pressure lowers as it kind of speeds up, goes across the both the top and bottom surface of the airfoil. But you'll notice you can see kind of a more dense, darker blue, so like lower pressure region on the top. And this makes sense because this is a cambered airfoil. So even at zero angle of attack, which is what our scenario is here, you can see that it's going to be a little bit of a higher pressure on the bottom surface in general. With that higher pressure than on the bottom and lower pressure on the top, your pressure gradient wants to go from high to low. So you're going to have a force that's going to be pushing upward. That's your lift force. So in this case, we'd actually be able to find a lift force on here if we wanted to. It's not part of the project, but I might even do it when we look at the force report. I hadn't really considered that, but we might take a look at that. Yeah, this looks exactly like what we would expect. So let's just go ahead and move on to velocity. Display. Yep, same thing, sort of thing. You can see the no slip condition. You can see velocity accelerating into the test section, yada, yada, yada. Same sort of thing we've seen before. And now if we look at the right around the airfoil, awesome. So you can see again, kind of like what I was talking about, kind of your stagnation point. You can see it get really blue if you really zoom in. It starts to get really dark blue right around there. And you've got like a no slip condition kind of around the airfoil too. So you can see your velocity kind of goes to zero around there. You get a little bit of a boundary layer type of thing right around it. But let's see. There we go. You can see a very, 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 very small wake region kind of behind, not really much of anything. You can see the flow is going to be going slightly higher speed on the top surface. But yeah, I mean, this is basically exactly what we'd expect for this. So this is a good solution. And then before I move on to looking at the streamlines, I'm going to stay on this page so we can look at the force report. So let's go ahead and take a look at our drag. It's going to be the same thing as we do before. We want the wall surface body. And in the X direction to get drag force. Let's take a look at it. So you can see exactly what we would expect, basically. Pressure drag's a lot lower than it was for any of the other bluff bodies, like the last one that I did in the other video. But you can see viscous drag is dominant, so it's greater than the pressure drag by it's over double it. And this makes sense. It's exactly what we would expect because it's more of a streamlined object. So you're going to get more skin friction drag. Perfectly reasonable. And you can see it's really pretty low. Makes sense because it's not, like I said, it's not that bluff body. It's obviously designed to go through air and have a pretty low drag coefficient because it's an airfoil. So that makes sense. Everything looks good. Just for our own curiosity, I'm just going to check this out. Let's see if we can get the lift force and coefficient on here. Yeah, so you can see obviously it's dominated by pressure. That makes sense. We're looking at total mainly is what we're going to look at. So you can see there is a net lift force generated. I should have looked at that on the other objects. You should have seen no lift created on like the cylinder or half circle that we did last time. And you can see it gives you a coefficient, but again, we would calculate that by hand. So as a reminder, when we're doing that drag force coefficient, you would take the drag force, divide it by the dynamic pressure in the test section. Again, use your calculated value for the velocity in the test section, just like as a constant value. And then you would multiply that in the denominator by chord length in this case. So it was diameter for the cylinder. In this case, it's chord length. And again, this will give you the drag coefficient per unit span since we're working with 2 dimensions. So chord length would be the critical length basically that you would be looking at in this case. So awesome. Okay, last thing, we'll try and go through this pretty quick, is to do the streamline again. It's literally the same thing. Honestly, I probably shouldn't. I'm just going to show it just so we look at it, but I'm not going to tell you again how to do it because we did it before. It's going to automatically generate once we get in here, and once it loads, but it's going to look literally the same. You do the same exact thing to get it as we did before. So if you need to look back at the last video, I think I explained it in part 1, but it should generate here for us in a second once it gets everything pulled up. Yeah, here we go. We got a streamline pattern. So let's maybe zoom in on this a little bit. Let's see. Yeah. So you can see, your velocity increases a good bit over the top surface, doesn't accelerate quite as much on the bottom surface. Again, that's what creates that pressure gradient that creates lift. You can see it slows down right at the tip of the airfoil. And there's this tiny, not really even a wake region. You can't really call it that because there's not like hardly any. There's very little, relatively speaking, very little pressure drag, but just like a slowed down velocity area. Just after the trailing edge. But yeah, honestly, this looks exactly like what we would expect. You can zoom in a little bit. I probably should add a little more points just to get slightly better looking pattern there. But yeah, this gives you the gist of what you're looking at. So yeah, I think that completes this second video of the project. So I think I'm done here, and hopefully this helped. Yeah, I think that's a full explanation for this project too. Thanks for watching.